Welcome back to another episode of Data Dynamics, where we dive deep into the world of data architectures, processing, and the fascinating technologies that shape our digital experiences. Today, we're unpacking some complex concepts around event sourcing, stream processing, and the challenges that come with managing data in a rapidly evolving landscape. So grab your headphones and let's get started. Let's kick things off by discussing the relationship between event logs and application state. In data management, the debate between normalization and denormalization often feels never-ending. However, if you can effectively translate data from a write-optimized event log to a read-optimized application state, this debate becomes less critical. Denormalization can actually make a lot of sense in these read-optimized views. A great example of this is Twitter's home timelines. Picture it like a mailbox filled with recent tweets from the people you follow. Here, tweets are duplicated across multiple timelines, but a fan-out service ensures that this duplicated state stays in sync with new tweets and changes in following relationships. While event sourcing and change data capture have their perks, they come with a significant downside: the asynchronous nature of event log consumers. This means that when a user writes to the log, they might read from a derived view and find that their write hasn't been reflected yet. This can lead to confusion and inconsistency. We touched on potential solutions to this issue in a previous episode, particularly the idea of reading your own writes. Next, let's delve into how we append events to the log. This process requires a transaction that combines writes into an atomic unit. To achieve this, you either need to keep the event log and the read view in the same storage system, or use distributed transactions across different systems. There's also an approach involving total order broadcast, which we'll explore in a future episode. Now let's tackle concurrency control. Many multi-object transactions stem from a single user action that requires changes in multiple locations. With event sourcing, however, you can design events to be self-contained descriptions of user actions. This means that a single write to the log can be both atomic and straightforward. If the event log and application state are partitioned similarly, a single-threaded long consumer can process events without needing to manage concurrency for writes. The log itself defines a serial order of events, which reduces the unpredictability associated with concurrent transactions. Interestingly, even systems that don't adopt an event-sourced model often rely on immutability. Many databases use immutable data structures to support point-in-time snapshots, and version control systems like Git depend on immutability to maintain a history of changes. But how practical is it to keep an immutable history of all changes indefinitely? It largely depends on the dataset's churn rate. Workloads that mainly add data with minimal updates or deletions can easily maintain immutability. However, in scenarios with high update and delete rates, the immutable history can become unwieldy, leading to fragmentation and performance issues. Now let's address a crucial point: the need to delete data for administrative reasons. Privacy regulations may require organizations to delete personal information when a user closes their account or to remove erroneous data. In these instances, simply appending an event to the log to indicate deletion isn't sufficient. You actually need to rewrite history, effectively erasing the data as if it was never written. This concept is known as excision in Datomic and shunning in the fossil version control system. But truly deleting data is a complex challenge. Copies can exist in multiple locations, including storage engines and backups, making it more about making data harder to retrieve rather than completely impossible. So far, we've talked about where streams originate, user activity events, sensors, and database writes, and how they're transported through messaging systems and event logs. Now, let's explore what you can do with these streams once you have them. Broadly speaking, there are three primary options for processing streams. First, you can write the data from events to a database, cache, or search index. This keeps your database in sync with changes happening elsewhere in the system. Another option is to push events directly to users through email alerts, push notifications, or real-time dashboards. In this case, humans are the ultimate consumers of the stream. Lastly, you can process one or more input streams to produce output streams. This often involves a pipeline of processing stages, where streams are transformed or filtered before reaching their final destination. The code that processes these streams is known as an operator or a job, and it operates similarly to Unix processes and MapReduce jobs. The key difference with stream processing is that streams are unbounded. They never end. This characteristic has significant implications. For instance, sorting doesn't apply to unbounded datasets, and fault tolerance mechanisms must adapt accordingly. With batch jobs, a failed task can restart from the beginning. But with a stream job running for years, that simply isn't feasible. Stream processing has traditionally been used for monitoring purposes. Organizations want to be alerted to specific events, such as fraud detection in credit card usage, monitoring trading systems for price changes, or tracking machinery status in manufacturing. These applications require sophisticated pattern matching and correlation. This brings us to complex event processing, or CEP, a methodology developed in the 1990s for analyzing event streams. CEP allows you to specify rules to search for patterns in event streams, much like using regular expressions for character patterns in strings. CEP systems often utilize high-level declarative query languages like SQL or graphical user interfaces to describe the patterns of events to be detected. When a match occurs, the engine emits a complex event with the details of the detected pattern. Unlike traditional databases that treat queries as transient, CEP engines store queries long-term and continuously process incoming events to find matches. Some implementations of CEP include Esper, IBM InfoSphere Streams, and TIBCO Streambase, among others. Distributed stream processors like SAMZA are also beginning to support SQL for declarative queries on streams. As we wrap up today's episode, we've explored the intricate relationships between event sourcing, stream processing, and the challenges that come with managing data in real time. From the importance of maintaining consistency to the complexities of immutability and deletion, it's clear that the world of data is both fascinating and intricate. Thanks for tuning in to Data Dynamics. If you enjoyed today's discussion, make sure to subscribe and join us next time as we continue to explore the evolving landscape of data technologies. Until then, keep questioning and keep learning.